In this project, we will learn about shift registers and how they work. We will introduce the shift register to control our 4-digit 7-segment LED, and will show how generally shift registers are handy in that they can reduce the number of pins we use from our microcontroller. Let's take a look at the objectives. By successfully completing this project, we will have mastered the following items. You will understand what shift registers are and how they work, and we will see how a shift register can be used to control our 4-digit 7-segment LED. If you are ready to begin, let's get this project started. Here are the parts we will need: an Arduino Uno, a USB cable, a breadboard, a 4-digit 7-segment display. We are using a common anode display, but you can use a common cathode display. You'll just have to be wary of the polarity changes in the wiring configuration. An 8-bit shift register. We'll be using the popular 74HC595 model, 7 220 ohm resistors, and connecting wires. Let's first delve into shift registers and how they operate. The specific shift register we will be using in our project is the 74HC595. It is an 8-bit serial in parallel out shift register and has 16 pins. But more about that in a short while. So, what are shift registers? Well, they are often used for the purpose of saving pins on a microcontroller. Data is shifted onto the register by setting the appropriate logic on the serial in pin and toggling the serial clock in between. After the bits are set, the latch pin, or the RCLK pin on this diagram, is toggled and the serial outputs are sent to the output pins. Hence, we are sending in data serially, and eventually all the data can be accessed in a parallel fashion on the output pins. Shift registers can also be connected in a cascading fashion so that shifting occurs from one shift register to the next. Since data can be sent in serially, less pins can be used to transmit the data. In fact, only 3 pins are needed: the serial in, the clock, and the latch from the microcontroller. Take a look at the diagram. Let's say our serial in signal is 1, or high initially. After one clock cycle, Q0 will be high. After a second clock cycle, that bit is shifted down and Q1 will be high. After a third clock cycle, again the bit is shifted down and Q2 will be high. And after the fourth clock cycle, that bit is shifted down and Q3 would be high. Let's get the picture? In that way, we are serially sending data in and it is being pushed along to the output pins. After 8 clock cycles, we'll be able to take that serial data that was sent in and access it parallelly from all the outputs at once. After all the clock signals are sent, at this time, if the latch is toggled, the outputs can all be retrieved from the output pins, resulting in a parallel out retrieval. Let's quickly take a look at the pinout of the 74HC595 8-bit serial in parallel out shift register. Our first output can be retrieved from pin 15, which is Q0, and then we have pins 1, 2, 3, 4, 5, 6, 7. We'll be able to receive outputs Q1 through Q7. So that will be 8 bits or 1 byte. Pin 8 is connected to ground, pin 16 to VCC, pin 14 is the serial data input pin, pin 13 is an output enable, pin 12 is our latch pin, pin 11 is our clock pin, and pin 10 is a master reclear pin. Pin 9 which is serial out, and that's used if we want to cascade several different shift registers. Let's take a look at this circuit diagram. As you can see, it's quite a lot of wiring, but to help make things a little more straightforward, the cheat sheets on the left-hand side of the circuit diagram will assist in how we wire up the circuit. The first one shows all the pins from our shift register and the corresponding connections on the 7-segment display as well as on the Arduino. Specifically, if we're looking at only the pins that are connected to the 7-segment display, that's in our second cheat sheet. And finally, remember, we'll need to individually control each digit on the 7-segment display. So that wiring from the Arduino to the display is shown in the third cheat sheet. Okay, let's go ahead and connect our circuit for our 4-digit 7-segment display with the shift register. This is the shift register that we'll be using, the 8-bit shift register. As you'll notice, there are 16 pins, 8 on one side and 8 on the other side. And when you're dealing with ICs, in order to determine where your pin 1 is, there's this indentation at the top of the chip. Typically, when that is at the top, to the left of it will be your pin 1. Will go all the way down to your pin 8, pin 9, come all the way back up to your pin 16. So that's handy to know when you're wiring up ICs. Also be careful with the actual pins for these ICs. They're delicate, so be careful when you're putting them in and taking them out of the breadboard because they can be bent easily and break off. Alright, so we'll go ahead and put our IC shift register in our circuit. As you can see, I left the resistors here. These are just 7 220 ohm resistors from our last wiring to make things go a little quicker. So you'll put these in and you'll put in your shift register. Next, I'll include the 4-digit 7-segment display. Just gently push it in as a reminder so that you're able to see the pins. Okay, let's go ahead and start with our shift register. So first, from pin 1 of the shift register, I'm going to go to the first resistor, and the other end of that resistor is going to go to pin 7 on the 7-segment. Okay. Next, second pin of the shift register goes to the second resistor. The other end of that goes to pin 4. Third pin goes to the resistor, and then that goes to pin 2 on our 7-segment. Fourth pin goes to our resistor, and that goes to pin 1. Fifth pin goes to our resistor, the other end of that resistor goes to pin 10, the sixth pin goes to pin 5. The 7th pin is unconnected. Pin 8 is grounded. So I'll make that ground connection now. And before we forget, let's connect ground. Or I should say first 5 volts to the 5-volt rail on the breadboard. And our ground to ground. Alright, so continuing on, pin 9 on our shift register is unconnected. Pin 10 goes to 5 volts. Alright, so I'll make sure that's connected to 5 volts here. Pin 11 goes to pin 7 on the Arduino. Pin 12 goes to pin 8 on the Arduino. Pin 13 goes to ground. Pin 14 goes to pin 6 on the Arduino. Pin 15 goes to pin 11 on the 7-segment display. And finally, pin 16 is connected to 5 volts. Alright, so just a few more connections for our 7-segment display. Pin 10 on the Arduino goes to pin 12 on the display. Pin 11 on the Arduino. Goes to pin 9. Pin 12 on the Arduino goes to pin 8. And finally, pin 13 on the Arduino goes to pin 6 on our display. Phew, that was quite a lot of wiring. And when you're done, remember, push in your 7-segment display. So I would highly encourage you to, take your time with this wiring. Make sure you get everything correctly wired up because it's quite a lot of wiring. But take your time and double check your connections so you don't run into any issues later on. Okay, let's go ahead and upload the code for our shift register and our 4-digit 7-segment LED. I'll open up the serial monitor here as that's loading up. Okay, so again, enter a number between 0 and 9999. The difference between this circuit and the previous one was we're using a shift register here to actually take the input serially and shift them out from serial in, parallel out, and display that on the 7-segment LED, 4-digit 7-segment LED. So I'll enter a number. Let's say 2559. Just picking some random numbers here. And as you'll see, that shows up on the display. Enter another number, 3267. Okay, that shows up. And I'll do a final number, let's see, 8993. All right, so there you go, and it shows up. So our circuit is working. So we will make a small modification to this circuit to complete our stopwatch project. So now our shift register is working in conjunction with our Arduino to control the 4-digit 7-segment display. Okay, let's take a look at the code for the circuit with our shift register. So we've seen these initial setup variables before in our previous circuit, so I'm going to go over those. Then we have our byte of mappings for numbers. Next, we have a digit vals global variable, and we'll see what that is shortly, but essentially this is going to be populated with the byte representations of all these numbers. And we're going to use that because that's what we're going to send in serially to our shift register, depending on the particular number we have to display, in order to get that parallel out. So we'll see how that's populated in a second. Next, we have the shift register pins. So pin 8 is going to be the latch, pin 7 is the clock of our Arduino, and pin 6 is the serial data in pin. So those are the connections that we made. In the setup function, we've seen some of the setup before. Then we define the shift register pins as outputs, the latch, data, and clock pins. We have to set up our byte array, and we call this set digit vals function. And this is what I was referring to. Essentially, what we're doing here is we're looping over our initial digits array, and we are converting that into a binary number. So for each value in the array, and that's our array at the top, okay? So for each value, we're looping through, getting the individual bits, and we're creating a binary number, which is a byte, and that's going to be sent to our serial in when we are sending information to the shift register. So that's all this function does. Bit set and bit clear are used to set a binary bit, or clear one appropriately. It takes in that byte, and next would be the actual index in the byte that you want to set, meaning set it to 1, or you want to appropriately clear it, setting it to 0. So at the end of this function, which is run only once in setup, we're able to set the digit vals to the appropriate binary formats to display or light the appropriate segments on our 7-segment display. Okay, so let's move into the loop function now. So if we get input from the user, again, we've seen this before, we read the string in and we get the character. First character is the input that character at 0, character at 1 for the second one, and so on, because remember the indices are 0-based, and we convert those to integers. We've seen this before. We call the update display function next, passing in the digits we want to display. This update display function looks like the same function we've seen before, and we call set segments digit 1, digit 2, digit 3, and so forth. The only difference in this program is how we implement our set segments function. So we're going to take a look at that now. So here's our set segments function. So initially we write our latch pin low. We perform a shift out on the data pin. The shift out is an Arduino function that is used to do that serial communication. The first argument is the data pin that we're shifting the data on to the actual shift register. Next we have the clock pin. And here the third variable is whether we're doing the least significant bit first or most significant bit first. And finally, here is the actual byte that we're shifting in serially. And again, based on the number we want to display, we have already populated this digit vals array, so it will return to us the appropriate byte we want to shift in to light the segments on the LED. And then we write to the latch pin high. This is actually going to make that output available on the output pins, and that's what's going to set the appropriate segments on the LED display. Okay, let's look at the documentation for the shift out function. All right, so I'll bring that up here. And as you'll see, it shifts out a byte of data, 1 bit at a time, starts from either the most or least significant bit. So if we look at the syntax, remember we're passing in the first argument is the data pin, the second is the clock, and the bit order is that value that could be most significant bit first or least significant bit first. So that just determines the order in which you want to shift out the actual byte, and then finally the value you want to shift out, right? And the value is a byte that you want to shift out. So very straightforward function, and this is important for us to use our shift register because the Arduino is able to use that clock pin to increment and shift the bits out one by one until we're ready to access it from the output pins in a parallel fashion. So without this function, it would be extremely difficult to integrate with our shift register, but this makes it pretty handy for us. To summarize, in this project, you learned how shift registers work, and we used one to send output to our 4-digit 7-segment LED. You were also introduced to the shift out function, which can be used to shift out a byte of data 1 bit at a time. In part 3 of this project, we will make a small modification to the circuit to complete our stopwatch. Let's finish this up.